Okay, students, start solving these questions. They are the questions based on chemical bonding and coordination compound. They are the mixed questions, but good level questions are there. Okay, so please try attempting these questions. Starting, some questions are single choice correct. Any problem in first question? Which pair of the molecules have hybrid highest occupied molecular orbital? So what will be your answer? Any problem in understanding this question, guys?
What is meaning of hybrid HOMO?
Hybrid HOMO means the molecular orbitals are hybridized and the highest occupied molecular orbital is actually a hybrid orbital. Like you can think of wherever sp mixing takes place, sigma bonds are formed by hybrid orbitals, right?
Where is the answer D option?
No. See, try to think over where sp mixing takes place. In what cases sp mixing takes place? Like in electrons less than equals to 14.
Or less 14 electron system or
Yes, less than equals to 14 electrons. In such cases, sp mixing takes place, except a hydrogen molecule. Okay, there is no need of any bond formation in case of hydrogen from sp mixing, right? Okay. So whenever you find that question is coming from molecular orbital theory and it is asking the bonds are formed by hybrid orbitals, just go through the sp mixing. You already know sp mixing पर questions आए हुए हैं. Okay, so इस टाइप का question हम expect कर सकते हैं कि कहाँ पर homo hybrid हो सकती है. Okay, so we know that in the case of nitrogen, the highest occupied molecular orbital is sigma HOMO. Okay, you can write the configuration. Fine. The configuration in which highest occupied molecular orbital in nitrogen is a sigma, right? And in the similar case, because the other diatomic molecules of the same group also follows the same sequences in their valence shell, therefore the most probable answer is B, right? Now getting the idea? All of you please reply.
Yes, sir.
See, F2O2, they are greater than 14 electrons. H2, there is no sp mixing applicable. Only in the nitrogen, there is sp mixing applicable in the given options. And similarity with the P2, it will also follow the same N2. Okay, so here the correct answer is B. Hint is sp mixing. Can we move to the second question, guys?
How is sp mixing possible in P2?
See, sp mixing, like the hybrid orbitals in the nitrogen, they are mixing 2s and 2p. In case of phosphorus, they will be 3s and 3p.
Okay.
Okay. Let us move to the second question. Here, just read out the question. It is single choice correct. A graph is given to you. The correct answer is option C. What is the explanation? Like boiling point variations when we go in the hydrides. Like first of all, consider that A to D. Okay. So they are matching with H2O, H2S, H2SE, H2T, because in these cases, H2O is having hydrogen bonding. H2 molecules will have hydrogen bonding, so their boiling point will be large comparative to the lower hydrides. Okay. But in case of H2S, H2SE, H2TE, they are having a similar type of forces of attraction, like dipole-dipole attraction they will have. They are not considered in the hydrogen bonding. So hydrogen bonding is a relative stronger forces of attraction. So H2O will have maximum boiling point and H2S, H2SE, H2TE will have comparatively lower. But among these three, the boiling point order depends upon the molecular mass because they have similar type of forces of attraction, right? So the actual order for this will be H2O, then H2TE, then H2SE, and then H2S. This will be the actual boiling point order. So the graph is actually correct because A is actually highest in this, and then B, C, D are increasing in such a manner. Okay. So this is the idea, and this takes place in case of HF, HCl, HBr, HI also. So E to H, because E is HF and HF is having lower boiling point than H2O. The graph is according to the boiling point difference between H2 and HF. HF, HCl, HBr, HI, again the same reason. HF will have higher boiling point because of H bonding. HCl, HBr, HI, their boiling point difference will be proportional to their molecular mass. So again the graph is correct. F, G and H, they are coming upwards. Okay. Now we come to I to L. So I, J, K, L. The same pattern is not being followed because none of the hydrides can show hydrogen bonding. CH4 also cannot show hydrogen bonding. SiH4, GeH4, SnH4, they all have van der Waals forces of attraction. When molecular forces are same, it will be proportional to the molecular mass. So it will continuously increase the boiling point. In such a manner, continuous increase in the boiling point takes place. And in inert gases also, continuous increase in boiling point must take place. So M2P is also correct. The false is the third line is false actually, I to L. The graph should come like M2P. M2P जैसा ही ग्राफ बनता तो वो भी करेक्ट हो जाता. Okay. So यहाँ पर incorrect match पूछा था आपसे, तो answer will be C. Okay, fine. Any doubt here? Clear, not clear? Reply you can do. You can say clear, not clear. Okay. Here they are asking the incorrect statement about this complex. Everyone is getting the answer?
Yes, sir.
Okay. So the correct answer is C. Okay. Any doubt? Anybody needs explanation?
Sir, isn't it sp2d hybridization?
No, this is not sp2d. This is dsp2 only, because it is using its inner d orbital. That one electron which is present in as a d9 configuration, that one unpaired electron will go in the higher excited state, and we can make vacant that d orbital which is inner. Okay.
Yes, sir.
Okay. So hybridization is dsp2. Deep blue color is a general point. We know, everybody knows that. And C option, it acts as reducing agent due to presence of unpaired electron. See, unpaired electron is also present here. That is correct. Point is correct that unpaired electron is present. That unpaired electron will be present in a higher excited state because it have to vacant that D subshell. But it will not act as a reducing agent. Why so? Because copper +2 is a very stable oxidation state and it never goes to copper +3 actually. In such a situation, we can directly say that copper +2 will never go to copper +3 situation. Okay. Therefore, this is actually a wrong statement. अगर reducing agent के बारे में नहीं लिखा जाता तो हम बोल सकते थे yes, unpaired electron तो present है and it is present in higher form, higher excited state. Okay. So answer is C. Good. Fourth question, please attempt.
A option.
Yes, in the last class also, in the short interaction, we revised that Na2C2O4 upon heating, it gives us Na2CO3. Na2CO3 will not decompose further. And in the cases of oxalates, we get a CO and a CO2, but we also get carbon over here. That is the exceptional portion. Okay, that is the exceptional portion. So in such a situation, we can say that Na2O will not form because Na2CO3 will not get decomposed into Na2. From here, we do not get CO2. We get CO2 directly from the oxalate anion. Okay, so answer is actually A because it is asked that not obtained. Okay, so answer is A. Next question.
C options.
The C.
Of the following species exists at room temperature.
EI.
Take at least 1 minute to confirm the answer, because sometimes in organic, what we see that we actually have knowledge of all the options, like at different places we have studied that whether species can exist at room temperature or not. But you should give at least 1 minute to IOC question also.
Option D.
Okay. Everybody is getting the answer. Idea लग रहा है इसमें क्या करना है? Please give your answers. Some of the students have given the answers. Rest of the students, please mark your presence in this question. What is your answer?
Option D.
Yes, it is very straightforward question because you know that PCl5, PBr5, PI5 do exist at room temperature. So answer is very straightforward. The reason for the others to not existing is important because this question can be framed in a MCQ manner also, that which do not exist at room temperature. So what is the reason why SH6 do not exist? Why FeI3 do not exist? Why xenon F3 minus do not exist? What are the reasons? I want your inputs. Please tell. Any one of you. About option A. Who want to say about option A? You might be knowing, but I want your interaction. That's all.
Hydrogen
Hydrogen is
not
a small
that
atom,
much.
Hydrogen is small atom. Yes.
so high repulsions around the sulfur atom.
If it is small, then how it will create a high repulsions? It is a small, no? So how it will create a high repulsion? Please tell me.
Since all the electron pairs will be close to each other, the
Okay,
bonded electron pair.
Bonded electrons will be closer to sulfur.
Yes.
Okay. Any other explanation for option A? Anybody else?
So electronegativity of sulfur is higher than hydrogen, so it cannot have oxidation -6. So it will not be present at room temperature.
Sulfur cannot have oxidation state -6.
Yes, sir.
Okay. See, according to NCERT, or we can say that SF6 do exist, HH6 do not exist. Sulfur can form 6 bonds easily with the elements like fluorine. But with hydrogen, what is the problem? That due to the negative oxidation state on the sulfur, sulfur is having actually a partial negative over here in the case of sulfur hydrogen bond. So in this situation, what happens? It's a 3s and 3p orbitals cannot be get combined with the 3d orbital, because in the case of hybridization, the intermixing is important for bond formations. So electrons which are present in d subshell, because obviously it will be using its d electrons, the gap between 3s, 3p and 3d, that gap is big between 3p and 3d. So if sulfur is having partial negative charge, the orbital will further go at the higher level, so its expansion will take place. But in case of sulfur connected with fluorine, it will be having partial plus and its contraction will take place. So when contraction will take place, 3D will come at a comparable energy level and intermixing will take place. Because in such situation, we are going to do sp3d2 hybridization. sp3d2 hybridization takes place only when the central atom is having partial positive charge due to that contraction of the orbital. So in the D case, D subshell case, if expansion is taking place, the electron will further go to the higher energy level and hydrogen cannot form bond in that situation. And also by thermodynamic means, we can say that the excitation energy will be more, because the electron going into the higher energy level will require higher energy. Okay, so non-participation of a d orbital in case of SH6 is the main reason. Some of the students had said it is correct that S is having partial minus, so it will be difficult to form the bond. The actual reason is non-participation of d orbital. Okay, and anybody who wants to say about FeI3, why it is unstable? मैं यहाँ पे लिख देता हूँ non-participation of d orbital. Yes. Similarly, pH5 also does not exist. Why Fe(I3) do not exist at room temperature? Any inputs from your side? Anybody?
I
Who is
minus is
pretty
good
much
reducing.
confident?
I3 minus.
Fe(I3) is unstable. Why?
Because I3 minus, it exists as I3 minus and Fe+1 is unstable.
I minus is good reducing agent. Reduces Fe3 plus 2.
Yes, actual reason is that Fe+3 can act as a oxidizing agent and I minus is acting as a reducing agent. I minus is a very good reducing agent. So in this situation, intramolecular redox takes place. Fe+3 goes to Fe+2. The compound forms FeI2 plus half I2. Okay. Getting the idea, it will be intramolecular redox. Therefore, Fe(I3) will not exist at room temperature. Again, some other compounds having iodides like PbI4. PbI4 also do not exist at room temperature because of the similar reasons. And such cases arises due to I minus only. When higher oxidation states are present and I minus are present and tendency to go into lower is there, then I minus will reduce that particular ion. Okay. So finally, Fe(I3) at room temperature is unstable. It converts into FeI2 plus half I2. Okay. What about C option?
Ions cannot exist free room.
Okay. See, in this situation, the lone pairs are 3. The fluorine we can place over here. Now, if we will be having 3 lone pairs over here. Okay. This will be the structure if we draw its structure. Right. But the lone pairs at 90 degree feels a very much high repulsion. That molecular geometry never exists. This molecular geometry never exists in which 2 lone pairs are at 90 degree with each other. Therefore, this is not existing. Okay. So I have given you the reasons. See, they are having different reasons. Non-participation of d orbital, intramolecular redox, lone pair at 90 degree, that molecular geometry never exists. And PI5, you know that it can exist. You might be solving some questions or theory you will be having like PI5, PBR5, they exist and their solid state structure also been asked. Okay. So correct answer is D. जो कि बहुत easily आ जाएगा आपका answer. You will get this answer very easily, but somehow the statements should be correct. Like if the question was asked that which do not exist at room temperature. Okay, let us move to the next question.
Sir, according to NCERT, PI5 is not mentioned in NCERT. Only FBr and Cl are mentioned for pentahalides of phosphorus.
PI5 can exist at a room temperature. Maybe in the solid state it will be existing. Okay. PI5
Yes.
solid converts into something else, but it is actually PI5. It can exist. NCERT is not mentioning it. I will check it. Okay. Somewhere it will be mentioned that PI5 can exist. Okay. I will check that. About the PI5, I think it exists. I've seen it somewhere that it exists, but if you are saying that, check in the NCERT, I'll check. Okay.
So is it option C?
Yes. Yes. Please, everybody confirm. Answer is C. Okay. Anybody needs explanation?
Between P and Q.
Between P and Q, it's a very simple explanation. Like it will be O2 2 minus with the anion it will be having, and they are just having the lone pairs, and anion repulsion will be there in this situation. So bond length will increase slightly. Okay.
Okay, sir.
Next questions are coming MCQs. Okay. Correct answers are A, B, and D. Okay. So what are the correct situations for A, B, and D?
CR2O3.
Yes. In this situation, Cr2O3 is missing, CRO is wrong. Okay, that's SO2, SO3 is correct. In B option,
No
FeCl.
reactions.
reaction will take place. FeCN3 will form as a precipitate. But FeCN3 is stable at room temperature. On slight heating, it can be converted into this situation. But at room temperature, it is stable. In C option, it is simple. Everybody knows this reaction.
Yes.
Okay. Colloidal solution of gold. Okay. In D case, again, it is on the normal heating, it will not break into CO. It will remain as CuO. Okay. So simple inputs are there. So answer are incorrect options are A, B, and D.
CD, sir.
Sir, C and D.
Okay. Any other answers, or somebody needs time? Take your time. Take some more time.
Sir, C.
It is MCQ. Okay. More than one correct. Okay. So the idea of the question is like B2H6 with the CO. When we warm it slightly, it will undergo symmetrical cleavage. Okay, and symmetrical cleavage actually takes place when we are having weak donors, like weak Lewis bases. Okay, so B2H6 undergoes unsymmetrical cleavage in strong donors. Okay, so that is the difference that we should know, that weak donor ability and that strong donor ability. Both statements are given. So one statement will be actually false, that symmetrical cleavage तो होगा, but donor ability अच्छी नहीं थी CO की, इसी वजह से symmetrical हुआ. So weak donor ability of B2H6. A is correct. C is actually wrong. And then what adduct will form? The adduct will be like BH3 and this CO, or we can simply write that BH3 dot CO. Okay, so symmetrically it will break. Okay, and here CO is giving the electrons to boron and not accepting the electrons. Okay, so whenever CO is a donor, carbon monoxide is having bond order 3, right? So isolated carbon monoxide is having bond order 3. When it becomes only a donor, its bond order actually increases. Okay, like you might be knowing that exception that when CO to CO plus conversion takes place, actually bond order increases, right? Everybody knows that exception, that when CO to CO plus goes, actually bond order increases, bond length decreases. So here also CO is becoming a donor. It will be having a donating ability here, but it is weak. But then also it is having a slight donating tendency, which will increase its bond order. So here CO bond order will be actually greater than 3. And a free CO molecule have bond order equals to 3. So B option is also correct. Bond order of CO in the formed adduct is greater than the bond order of free CO molecule. And boron, bond order of boron and carbon bond is formed adduct is 1, because this is a single coordinate bond, sigma dative bond. So answer will be A, B, and D. Okay, fine. This is the extra point which we are getting from the molecular orbital theory. When CO goes to CO plus, bond order increases. Here also it is donating, not accepting electrons. Okay, so CO is very important. You know that in molecular orbital theory also, explaining CO is a typical task and its behavior is like this. Okay. Any doubt here? Any other doubts here?
So, but trimethyl ammonia will undergo symmetric cleavage and ammonia will undergo unsymmetric cleavage.
In case of ammonia, it will go unsymmetrical cleavage. Yes.
But trimethylamine is stronger base than ammonia.
That is due to steric repulsion. Some of them are exceptions. Like being better donor also, NR3 plus NR3 goes symmetrical cleavage. Only those which are good donors and less steric, that will go
Yes.
unsymmetrical cleavage. Okay.
Yes, sir.
CO plus has a higher bond order than CO, then HOMO of CO molecule should be antibond.
CO molecule, please repeat the doubt.
CO plus has a higher bond order than CO, then HOMO of CO molecule should be antibond.
HOMO of a CO molecule is actually a non-bonding molecular orbital having slight antibonding characters. The HOMO is having slight antibonding characters. You might be knowing that NBMOs which are towards the BMOs having bonding molecular characters, bonding characters, NBMOs which are higher in energy have antibonding natures. So we are having a lone pair over here, which will be lying in a non-bonding molecular orbital. That non-bonding molecular orbital is having anti-bonding character because it is near to pi star.
So then bond order of CO cannot be increased while calculating number of bonding electrons.
So when that electron we are removing, it is removing from a orbital having slight antibonding character. Whenever electron will be removed from antibonding or orbital having antibonding character, bond order will increase.
Yes.
That is the reason. Okay. Anybody needs more time? Question. I think everybody can easily grasp the question language, that the complexes which are having unpaired electrons, first of all, you should focus on the options that whether they will be having unpaired electrons or not. See, B option Ni plus 2 will not have any unpaired electron. And in A option, it will be copper plus 2. So it will be having D9 configuration. And in option C, it will be cobalt plus 2. It will also be having an unpaired electron.
Sir, in B option, it is octahedral complex, so it will have unpaired electrons.
It will be having unpaired electrons. Yeah, right. Its hybridization will be sp3d2. Yes, yes. 2 unpaired electrons will be there. Okay. So it will be having copper plus 2 configuration, Ni plus 2, cobalt plus 2, and here cobalt minus. Okay. So what are the configurations? By how many electrons in D? Please reply quickly. Here configuration will be D9. In Ni plus 2 configuration will be
D8,
D8. In cobalt plus 2 configuration is
D7,
D7. And cobalt minus
D10.
D10.
D10. Okay. So configurations are over here. Okay. Fine. So in these situations, we are having the unpaired electrons D9, and it is like coordination number 5, and strong field ligand is there. So what will be the hybridization over here?
sp3.
sp3d or dsp3?
sp3.
That unpaired electron, if it moves in a higher energy level, it will get excited. Then the inner D will be vacant, na?
But energy gap is very large.
But that will be compensated by the ligands bonding and the lower energies. Bonding with the d orbital at a lower energy will compensate the energy of that excitation. So in order to form the stable inner orbital complex, that electron will get excited.
Okay.
Okay. So in this unpaired electron will get excited into the next higher vacant orbital, that is 4d. Okay.
Yes.
So A will be the answer. In this situation, D8 configuration is fine because we will be having T2G and EG configurations like this. And it will not excite these two electrons to vacant the inner orbital. Only one electron can get excited if we need one d orbital. But the hybridization will be then sp3d2. So no need of these electrons to go at the higher energy level. So they will remain in the 3d. They will not go to the valence shell of the central metal, that is 4, n equals to 4. Okay. So B will not be the answer. And in C also, this is coordination number 6. It will be using, in this case, a strong field ligand is present. To D2sp3 will be the hybridization. And to vacant that inner orbital, one electron will get excited at the higher end. Okay. Getting the idea of the question. And D10, no unpaired electron will be there. So answer is actually AC. Any doubt here? Anybody wants explanations?
The valence shell shouldn't be 3D.
No, because the valence shell means the electron can get to the higher energy level. Because it is going to the higher energy level, therefore that will be counted as n equals to 4. Because although 3D is the last because 4s is vacant, but 4s, 4p, 4d, they can be available for bonding. They are used by the bonding, na? D2sp3 or dsp3 you are using.
Yes, sir.
Fine.
Then option C, valence electron is in 3D.
Valence electron is in 3D. See, cobalt is already having D7 configuration. So D6 configuration will be here, and these two EG configurations are orbitals are vacant. So it will be D2sp3.
Okay.
So to vacant this one electron, this orbital, that electron going to higher excited state. And it is using D2 as P3, and then D will come. So the higher excited state in which electron will go, that will be 4D.
Okay.
Okay. So such type of questions are actually when we there is a condition of transference of one electron only. And what is that condition? That whenever one electron is unpaired and strong field ligands are present, see, strong field ligand should be present, and one unpaired electron is actually moving to the higher energy level to form a stable inner orbital complex. If stable inner orbital complex is not forming, then excitation will not take place. So for excitation of this single electron, inner orbital complex must be formed, and that is the case where we have strong field ligands only. These two conditions are there. Okay. So here in this case and in this case, both these conditions are actually getting applicable. Okay.
Sir, BCD.
So C and D.
Okay. First of all, let us discuss about the complex. What complex is forming here?
SCN6 minus, sir.
With cobalt or with the mercury, actually SCN minus is a weak field ligand. Okay. And Hg plus 2 is having better tendency to form complex with the weak field ligands. And cobalt plus 2 is having a better complexing tendency with that strong field ligands. So here cobalt plus 2 as a major product, cobalt plus 2 will be at the outer side of the coordination sphere, and HgSCN4 will be present here in the coordination. अब आप क्वेश्चन को सॉल्व कीजिए, 1 मिनट और दीजिए, अब आ जाएगा आंसर. ओके फाइन. अब आपका आंसर आ रहा है.
So B and C.
B and C, hybridization of the central metal is sp3. Color of the complex compound P is not due to DD electronic transition. Right? A also becomes correct now. The paramagnetic character due to its complex anion part. Okay, this will be incorrect. Okay, this will be incorrect.
Color isn't due to charge transfer.
Color is actually because of that cobalt +2 ion. That is paramagnetic. Unpaired electrons it is having. Okay.
Okay.
So color due to cobalt +2. And B is also correct. The central metal cation for the complex compound is Hg+2. So answer is B, C, D.
And sir, in this, how do we get to know that Hg2 plus has higher tendency to form complex with weak field ligands?
See, this is the observation that mercury +2 cation actually do not form a complex with a strong field ligands, right?
Yes.
Instead of that, it is having a complex formation tendency with a weak field ligand. Like I-, it can form complexes, right?
Okay, sir.
Color is due to DD transition.
Color is due to DD transition.
In CO2 plus, it has a possibility of DD.
But color of complex compound P is not due to DD electronic transition. Oh, okay. If the color of complex compound P as a whole, it is a complex compound P, is not due to a DD transition. You are saying that because in the cobalt +2 ion, the color will come because of the DD transition. Because that is paramagnetic. Yes. But if we are looking into this option, like color of the complex compound P is mainly due to cobalt +2, and cobalt +2 is having the color due to DD electronic transition. Yes, yes.
Will then be splitting in cobalt 2 plus without a
Yes. So cobalt +2 is at the outer side of the sphere. Mercury is in the inside of the sphere. That complex part will not having the color, and the color is coming actually because of the cobalt +2. And it will be having color due to DD transition. Cobalt +2 is having. Yes, yes, yes. So answer should be B and C.
Sir, charge transfer because of Hg+2 has no contribution.
No, it will not charge transfer to any ligand or any cobalt +2 will remain cobalt +2. They will not actually exchange their charges. Okay, the mainly color is due to CO +2 because the complex part is not having any color. Na? Complexing anion is not having any color. So paramagnetic character due to its complex anionic part is not there. That paramagnetic character is because of the cobalt +2. It will be colored. A complex as a whole is colored. Have some reasons like a DD transition can be there, or some ligand to metal charge transfer there, metal to ligand charge transfer is there. Okay, so DD electronic transition will be there in cobalt +2. Most probably it will be included because of cobalt +2. Okay, so there is a little bit problem in D option, that color of complex is coming because of that. What is the reason behind its color? The color is basically due to cobalt +2, and in that DD transition can take place. Okay, so better the answer correction is there. We will mark this answer as B and C. B and C only. Okay. DD electronic transition can be there in cobalt +2. Fine. I'm having the answer as B, C, D, but now I'm thinking that they have missed that cobalt +2 is actually colored due to DD electronic transition. Okay. Please try solving question number 11.
ACD.
Yes. Actually, very simple question. You have to identify the gas Q and then which of the following precipitates is or are soluble in excess of the gas Q solution? Okay, easy. Other students, please mention their answers if they need any explanations. Okay, no explanation required. Answer is actually A, C, and D. Anybody needs explanation?
Yes, sir. Please explain it once.
Okay. See, the gas Q is actually ammonia.
Yes, sir.
Okay. So gas Q, ammonia. Ammonia is also a strong field ligand. Okay.
Yes, sir.
So in such situation, ammonia forms complex with copper +2, Ag plus and chromium +3. It will form stable complexes with the D block cations. Okay, copper +2. So it is actually P block cation. It will not form complex with the ammonia. तो soluble करने का मतलब ये हुआ कि हमें इनके complex soluble complexes मिल जाएंगे. Okay.
Yes, sir.
Okay. So D block cations with excess of ammonia forms complex compounds. The condition of complexation. Okay. Next. Next is a paragraph. Again, it is very easy. Just try it once. In the first point, you can recall that what is happening over here. Yes. A water insoluble compound P on heating gives QRS, and substance Q is also water insoluble and changes color on heating. See, these are sulfates or oxalates. They will be giving somehow their oxides, right? And the color changing property among these oxides is of PbO only. PbO is red and it is yellow when it is hot. Okay. So the indication is all about A option. Because oxalates are there and sulfates are also there. We know that in situation FeSO4, we get three products, Fe2O3, SO3, and SO2. But FeO is not having a color changing property upon heating. So the whole sequence will change when we observe that second line, changes color on heating, PbC2O4. Okay. And then we can know that QRS, PbO will be there, Q, and R and S maybe CO2 and CO gases, because C2O4 ki heating karna hai. So here boiling point of R is greater than S. That is because of the mass factor. CO2 is R and CO is S. Okay, both are gases. So CO2 on excess of NaOH solution, it will form Na2CO3. Okay, form Na2CO3. So here PbC2O4 upon heating will go PbO, CO2 and CO. Okay, Na2CO3 solution when in the let's say it's aqueous solution is there and copper +2 copper nitrate is there, we will be having its basic carbonate CuCO3 CuOH whole plus basic carbonate, that is malachite green color जो और भी होती है उस तरीके का ये ग्रीन कलर यहाँ पर शो करेगा. तो आंसर्स आर ए एंड ए. ओके.
Yes, sir.
Water insoluble and also colored. Okay. So answers are PbI2, Ag2O, PbO, and CH3C. It will be like Ag3PO4. These four will be water insoluble and also colored. Any explanation you need in this question?
Yes.
All solubility points and colors. Okay. See how to solve such type of question. Like we have to check for water insoluble and also for colored. First of all, check the solubility portion. इनमें से कौन से water insoluble है उनमें पहले बात कर लेते हैं. Okay. तो जिन पे हम टिक करते हैं वो soluble है, क्रॉस करेंगे insoluble. So these are soluble insoluble, insoluble, soluble, soluble, insoluble, insoluble. Okay. Now out of them, colored PbI2 is yellow, Ag2O is brown, PbO is red, Ag3PO4 is yellow. Silver acetate is white. Okay. So colored means other than white. Therefore, we are not considering CS3COO Ag.
Okay.
Okay. Next question, 15.
Sir, what will be the color of the solution of copper sulfate 5H2?
Blue.
Okay. So 0.
No, answer is not 0.
X4, Y2.
Yes.
For answer 2.
Yes, sir. X4 and Y2.
Okay, final answer is 4. Anybody needs explanation? Question 15, any explanation? Anybody needs?
Sir, 4 or 2?
Answer is 2. Yes. X equals to 4, Y equals to 2. Answer is 2.
Sir,
Yes or no?
in 16, what is the use for that non-chelating complex statement?
Non-chelating complex means the all ligands present are monodentids and they are not chelating like.
Okay. More than one donation site is not there from the ligand.
Yes. Yes.
Okay.
6.
Yes. 17th answer is 6. Give the number of species in which CO bond order is less than 3. Carbon oxygen bond order is less than 3. So in metal carbonyl complexes, the CO bond order decreases due to synergic bonding, back bonding from the metal. So here the bond order will be less than 3. In this situation, scandium plus 3 is there. Scandium plus 3 will not have any d electron. So it will not do any back bonding, will not send any electron to the ligand's anti-bonding molecular orbital. So here simply we can say that a CO is a donor. CO can donate the electrons. It will not be having the bond order less than 3. Again, this will be having bond order 3. In CH3CO, this is acetone. The bond order is 2. In CO2 also bond order 2. In carbonate ion, bond order is 1.33. Mn2CO10 is also having the synergic bonding between CO and Mn ligands. So it will also have the bond order less than 3. VCO6 have bond order less than 3. And this is the complex that adduct like BH3 and CO, like BF3 and CO. In such situation, bond order will be greater than 3. So the bond order which are less than 3 are 1, 2, 3, 4, 5, and 6. Okay. Okay. Next question. Again, based on NIDMG, this is the second question. Based on its structure. 6. Yes, 6 is correct answer. Rest of the students, please solve question number 18. Again, these integer level problems are very simple. You have to just draw the structure of NIDMG whole twice.
Sir, in this, we have to find multiple answers for every name in the end, or everyone for particularly? Sir, your voice is not coming.
They are multi-correct.
Okay, sir.
Okay, anybody is having a doubt in question 18? The answer is 6.
Sir, in option C, it is AC or BC.
It is a BCAC. Like ACAC is acetoacetate.
Yes.
This is benzyl. This is phenyl acetoacetate, in which benzene ring is present.
Sir, PQT, QRST, PST, QRT.
Yes.
Sir,
Yes.
sir, how to check the T option?
P option.
No, sir, T.
P option. If the pH of the medium decreases, that means medium becomes acidic. Maybe the donor side gets protonated and no lone pair left at it.
Oh, okay.
Okay, fine. The answers are A, the answer is PQT. B, answer is QRST. C, answer is PST. And D, answer is QRT. Please check. Any doubt?
Sir, this H2 EDTA2 minus, in this EDTA4 minus, we occupied 2 minus.
EDTA 4 minus is the EDTA, and they are having that negative charge on the CW part, acetate part, right?
So we
And
take
if
2H2.
2 of them are protonated, then
Okay.
so mainly nitrogens are the donor and the anions are the donor in this situation, EDTA. Okay. Any doubt?
So RS, QR, and S, and then RS.
Okay. The answers are A, RS, BS, C, QRS, DRS. Any doubt? Check please. Fine.
Yes, sir.
Anybody needs any explanation here?
For
Okay.
B, why not R?
The thermal stability of that monohalide depends upon lattice energy.
But
Okay.
Br minus is a larger anion.
It is larger than that, but it is not polyatomic anion.
Okay, sir.
Okay. In case of polyatomic anion, thermal stability is inversely proportional to that polarizing power of the cations. But in case of monoatomic anions, it is directly proportional to lattice energy, whether size is big or not. You are asking for thermal stability, right?
Order
Yes, sir.
will be reverse for thermal stability.
Which option?
For B.
For B, thermal stability order is reverse of this.
Okay.
Okay, so this question was just to recall the trends of solubility and thermal stability of nitrates or carbonates and hydroxides. Okay, fine. Okay,
Yes,
guys,
sir.
I tried my level best to make such questions which will help you, which helped you a lot. So please, if you have any confusion, any doubt, want to ask anything, you can ask, and then we can end up the class here. Okay.
Sir.
Yes.
So I have a doubt in a PYQ question of 2017.
Okay.
So in it was given that a complex compound was given, MCl2.6H2O.
Yes. Yes.
And we reacted with excess HCl at room temperature.
Fine.
And it was given that it results in the formation of a blue colored complex. So how will we judge that which complex will
due to the color combinations which are mentioned in the theoretical portion of that question, it will be most likely cobalt. Okay, cobalt plus 2 ion. So if you study
Yes,
about
sir.
cobalt plus 2 ion, you will get the idea that how its color changes upon hydration. Okay. From
Yes, sir.
there you will get to know about the whole question, how it is going to solve. Okay. I'll include that question in the next session. Okay.
Okay, sir. Thank you, sir.
Okay, guys. Bye bye. Take care.